Welcome. We have another problem at the screen, and this is about finding the electric field at a point. And we have two parallel half planes. I'm reading the statement of the problem that we have two parallel half planes are uniformly charged with charge density plus sigma on the upper half plane and minus sigma on the lower half plane. Find the magnitude and direction of the electric field strength E at point M, which is at a height h above the edge of the half planes. The distance between the half planes d is small compared to h. So we need to solve it. But how can? This is the problem. Let me show you the side view of the system so that you can see the picture and recognize yourself. You can see both pictures, this picture with carefully and this picture. Here in this picture we have drawn the half planes like this. This is the distance d between them and h here. And I have taken something like this is a small strip of thickness or width delta x. There is a small narrow strip like this, and if you can think it like this, you can see this strip is like this shown in this picture, and this is its thickness. Its thickness is here, and that is delta x. And things are getting messy here, but we have to recognize them in our imagination and try to solve the problem. I'm going to use the formula electric field due to a long wire is something like lambda by 2 pi epsilon naught r, and r is simply distance, and this is obviously the long wire. This thing is the long wire, not the semi-infinite long wire. This is basically infinitely long wire, and we know for the infinitely long wire the concept is here will be the electric field like in this direction, and its value is given by this statement. So I'm trying to use this. How? This is a bit messy, but you have to be imaginative all the time solving this problem. And so since charge densities are given, charge density on this plate is sigma, and here it is minus sigma. So we need to solve the problem using lambda, but we have charge per unit area, and lambda is charge per unit length. So I'm going to relate first the charge per unit length lambda with charge per unit area density, simply writing this. Lambda will be equal to sigma delta x. Delta x is of course the width of this narrow strip, you can see here. And then the electric field due to this narrow strip will be something dE or delta U1, and this can be written as sigma delta x. Here in this picture you can imagine this this width like this, like this is a long wire, then you can write this statement sigma. Width is obviously a1 b1 is the width here, and by writing 2 pi epsilon naught r, or you can take either a1m or b1m because thickness is quite small. So I'm going to write something like a1m. This is the distance from here to point M. And in the similar manner, you can write the electric field due to this strip, that is A2 B2, and just write this in the same manner. Delta E2 equal to sigma A2 B2 divided by 2 pi epsilon naught, and in the similar manner you can write here A2M. And one more thing you need to find out, there is some kind of similarity here, and similarity is like similarity in this triangle. If you recognize this triangle M2 covering A1 then A2 and A2, you can see here that A1 B1 divided by A2 B2, that is going to be equal to A1 M divided by A2 M. A2 M. M. And so you can write here A1 B1 upon A1M will be equal to A2 B2 divided by A2M, and you can see delta E1 and delta A2 got same magnitude, but their directions must be opposite because one is created by positive charge and another by a negative charge of same charge density sigma, plus sigma and minus sigma. That means the pair of kind this kind of two long wires will create a net electric field equal to 0 at point M. What I'm trying to tell you that the fields of these strips mutually compensate each other, and this reasoning is valid for all pairs of strips cut out by the planes. These are planes basically MM1 and MM2, and the only strip KL which is very far away from point M and belongs to the upper half plane only, and it can be seen from this drawing at least that there is no paired strip for it on the lower half plane. So the required magnetic field E at point M will be equal to the electric field created by this strip KL. And you know, KL is very far away because they are infinite planes. So if you look KL from this point, it will be seem like this alpha angle is basically equal to 0 because this is very long. This is very long. That means infinity. So if you try to look at this KL strip from point M, this alpha will be very close to 0. So this KL strip is going to produce only this electric field, not this one at point M. And if you can convince yourself for this argument, you can write here that the electric field required here can be sigma KL. Sigma delta x is KL right now. KL will be quite small, very small, very small, because these two strips are infinitely long. So that means KL is going to be quite small, very much small. So you don't need to worry about much about KL looking big here. But this is not big. This is quite small, and you can write here rest of the things 2 pi epsilon naught, and the length and the distance you can write anything. I wrote it ln as r, and if you like to calculate length of KL from our picture, you can calculate something from symmetry, from not exactly symmetry, but from the similarity in these two triangles. You can calculate simply KL as BD upon H plus D, and you know D is much smaller than H, so you can approximately write it BD upon H. And in the similar manner you can calculate LM. LM will be from this triangle. You can calculate LM as under root H square plus B minus KL square. B minus KL square. Yeah, like this. And what was B in fact? Before considering anything else, you can see what is basically B. B is this length. This length. You can see here. Though B is infinity, so but still taking it a finite length. If you take it as a finite length, though it is infinite, so we will put B tends to infinity later. But so in from this triangle LM, you can see that LM can be simply written as H square plus B minus KL, length KL square, and that is going to be approximately equal to, since B is quite big, but I'm not going to put it as infinity right now, and I'm still looking for approximations, but I can still write this LM will be can be written as H square plus B square, and then the electric field we got here is lambda KL, and we got KL here and LM here, so that we can write the electric field as sigma BD divided by 2 pi epsilon naught H under root H square plus B square. We can write putting all the values, but we need to find out not the E but E parallel. You can see here parallel to this, we need to find out this thing, and this is obviously E cos alpha. So E parallel you can write here as E cos alpha, and put the value of cos alpha from this figure. This angle is alpha, or this angle is alpha, so you can put cos alpha equal to base by hypotenuse, and you will get the result for cos E cos alpha, like this is cos alpha, so that E cos alpha can be simply written as sigma B square D by 2 pi epsilon naught H square plus B square, and Now you can use b tends to infinity and divide b square divide by b square. Both the numerator and denominator can be divided by b square, and you will get the result that will be sigma d by 2 pi epsilon naught h. And I guess this is the required electric field there at point m. So there is approximation, not the real mathematics. And you can solve this problem by using real mathematics. Because if you try to do so, you will get integrations like the results coming in logarithm in the form of log, and then you need to write the expansion of logarithm, and you will definitely get to this result. But that is a long way to solve this problem, lots of mathematics. And if you use approximation, you will get it early and easily. So thank you very much for watching.